Okay, so I'm going to present a work about structured GANs written by myself and Lior. My name is Irad Peleg. Given some image-related challenge, here's what we often do. We add a CNN. We think carefully about the loss function and fit it to our needs. We train the network, and we're done. But in the case of GANs, loss becomes tricky. GANs are also known GANs are also known for instability issues. An alternative approach for modifying the loss function is modifying the network architecture. In this work, we present several experiments. In each, we define a task. We then explore ways of accomplishing the task by modifying the network architecture. Among our experiments are texture synthesis and tiling. We would like to create. Now I'm going to show you an example of creating a symmetric generator. So the generator gets Z, which is a 100-dimensional vector. Let's define the first 5 elements as Z prime, and the remaining 95 elements as Z double prime. Let's also define Zn to be the concatenation of negative Z prime and Z double prime. So our goal is to create a generator that satisfies the following condition. G of Zn equals the mirrored version of G of Z. So and from this definition, when we set Z prime to 0, the output G of Z will be left to right symmetric. So how can the net be rewired in order to create this symmetric property? Okay, so this is a simplified block diagram of DC GAN. It contains 4 components. And in this example, we'll talk only about G that has only 2 of them. So in the blue dashed line, there's the fully connected part of G. Let's call it FCG. It turns a vector into a tensor. And in the red dashed line, the CNN of G, it turns this tensor into an image. So our strategy will be to satisfy the condition on the output tensor of FCG. And the goal of CNNG will be to maintain this property while the output it received from FCG is gradually being changed and turned into an image. So this is the block diagram of FCG. Due to time limitation, I won't get into details, but it's on the poster. So moving on to the CNN part. The trick is quite simple. All we need to do is to enforce left to right symmetric kernels in the CNN. So in this demonstration you see in this slide, it doesn't really matter if you convolve before or after the mirroring. Also, nonlinearities like ReLU will not affect this symmetry property. So when we defined symmetric kernels, only 3 columns are defined, and the graph will duplicate it to 5 columns like you see here. It also means that less parameters are needed. So here we see some results. Z double prime remains fixed, and we interpolate on Z prime. Okay, so moving on to transfer learning on G. Z can be optimized in order to create similarity to a real image. Okay, this example was taken from BE-GAN paper. So as you can see, the results are good, but they are lacking similarity to the original image. So here you can see at the right column you see real images. At the column to the left you see the image generated when we optimize Z. And the other columns to the left, we just shift Z prime and create this rotation effect. So here we do exactly the same thing, but this time we also optimize G as well as Z. So as you can see, the images, the rotation effect is created, and the images are closer to the original version. So thank you all. Come visit me in the poster. That's it.